Let's look at some applications for Chapter 11 and make sure you have your equation sheet nearby so that it will be easier for you to follow along as I work these problems. Okay, so let's start with this problem regarding a ship's wheel, and we see the sketch right here. So we're told the radius of the wheel, and we're told two different forces acting on this wheel. So we see force 1 and force 2, and we see the angles they are acting at. So we want to find the torque caused by each force and then figure out which direction the wheel would turn as a result of both of the forces. Okay, so take a look at your equation sheet and you should quickly find torque. So let's calculate the first torque, which would be T1 equals R, tau 1, the force multiplied by sine theta. And we're going to need to determine whether this would be positive or negative. Recall that that is going to have to do with the direction of motion, so whether the wheel would be turning clockwise or counterclockwise. And if we isolate this first force, just imagine yourself pushing up right here. We know that this wheel would begin turning counterclockwise, so this is going to be a positive torque. We're going to plug our information in, and it's 0.74. And sorry about that. 72 newtons multiplied by sine theta, which in this case is 50. And when we do this math, we should find 41 Newton meters is our first torque. Okay, so y'all take a moment and find the second torque. Okay, so the second torque, and I hope you realize this, would be negative because if we isolate this second force, so imagine yourself pushing in this direction, we know that this would begin turning clockwise. So alone, this second torque is going to be negative. And this is sine theta again. Plug in all of your information, and you'll find that the second torque is negative 43 Newton meters. Now, if we want to know what direction the wheel will turn as a result of both forces, let's just add them together. So 41 Newton meters plus a negative 43 Newton meters is going to give us a negative 2 Newton meter torque. Well, we see that is negative, so what direction would this wheel be turning? Negative indicates that it would be turning in a clockwise direction overall. Okay, let's move on to the next one. Problem number 2. Now we are looking at a wind turbine. And I think y'all know what that looks like. It's like this. I'm just going to draw a very simple one. Something like this. Maybe it has more blades, maybe not. But it has a radius of 37 meters, and we know its moment of inertia. And we've been given the angular speed. So as the wind speed increases, we now have a net torque listed here. We want to know how many rotations it will take for that angular speed to increase all the way to 1.8 radians per second. And we've been given a lot of information here, but this isn't so bad. So we're going to find the rotations needed for the speed to increase to 1.8 radians per second. And then after that, we're going to find the linear speed of the tips of the turbine blades 27 seconds after that acceleration actually begins. So we are going to need some information. So take a look at your equation sheet and let's pick out an equation that might be useful here. So I found this one. But we are missing one of these pieces of information. So we know what our initial angular speed is, and we know what the final angular speed will be. We can figure out delta theta, because that would be our rotation. So we can figure this out. So we just need this acceleration. Well, do we have enough information to find acceleration? Yes, we do. So recall that the angular acceleration is the torque divided by the inertia, and we have both of those. So 1.6 times 10 to the fifth Newton meters divided by 8.4 times 10 to the sixth kilogram meter squared. And that is 0.019 radians per second squared. Okay, so now we have our angular acceleration. Let's rearrange this equation so that we're solving for the change in theta. And when we rearrange that, you'll get this. And then that's divided by 2 times the angular acceleration. All we have to do now is plug in our information. So we get 1.8 squared minus, so here's our final. 1.1 is our initial, so 1.1 squared. And we will be dividing that by 2 multiplied by 0.019 radians per second squared. So we'll find that that displacement is 53 radians. Okay, we can convert radians to revolutions. So 53 radians. And I hope you remember this too. If not, write this down on your equation sheet. There are 2 pi radians in a single revolution. And if we do this math, it would be, ooh, that's a point. Oh, that's terrible. Okay. 8.4 revolutions. So this would be your answer to part A. Now we need to find part B, and I'm going to have to erase this. Okay, so we know 8.4 revolutions, and we now have, and we calculated that angular acceleration. So if we need them again, we'll have them. Okay, so for part B, and if y'all want to take a moment and try this yourself, I think that'd be a good idea. And if you want to keep watching, that's fine too. So looking at that equation sheet, this equation is the one that's going to make the most sense now. We have the initial and final pieces. Oh, I'm so sorry. We're on part B. What is the linear speed after acceleration begins? So we need to find linear speed, but this equation is telling us about angular speed. So how are we going to get from angular speed to linear speed? Again, take a look at that equation chart, and that's supposed to be linear speed equals the radius times our angular speed. So we just need to calculate this, and then we can plug everything in and solve for linear speed. Okay, so angular speed is equal to, we need our initial speed, which was 1.1, and that's radians per second, plus angular acceleration, which we calculated 0.019 radians per second squared. And we have the time, which is 27 seconds. So we'll find that that angular speed is 1.6 radians per second. So let's find the linear speed by using this. So V is R times angular speed. Plug in what we know. We know the radius, which is 37 meters. And we know this piece of information because we just calculated it. And our linear speed comes out to 59 meters per second. Okay, so that's how you would solve part B. And erase again. Okay, so this one's going to be slightly more involved. We don't have an image, so we're going to draw one because this one is a little bit more involved. And if you would like to take a moment and try to sketch this on your own and then watch how I sketch it, that's fine too. So a cat is walking along a plank. So here's our plank. I'm just going to write cat. I'm not even going to, there you go. There's our cat. And the plank is supported by two sawhorses. And if you're not sure what that is, it's the little things that look like this. Those are the sawhorses, the supports. It says that the center of mass of the plank is this distance to the left of sawhorse B. And the cat has a distance to the right of sawhorse B. Oh, okay, so I did this correctly. So my cat is to the right of sawhorse B, and the center of mass is to the left. Well, I'm just going to label this A and B since I've already drawn my cat over here. We want to know what the mass of the cat is. So we're going to use all of this information to help us find the mass of our cat. All right, since we know everything seems to be happening around this second sawhorse, sawhorse B, we're going to call this our axis of rotation. And that makes sense because this is where our cat is very close to. And just think about the experiences you've had. If the cat's mass is over here, we know this end could easily start coming up this way if the cat, or if we added, I don't know, a second cat or a little bit more mass here. Okay. So we have a lot of things going on, but our net torque needs to be 0. So we need this to be true. Well, let's think about what's going on. We have a couple of things happening. The obvious one is that we have this cat whose weight is causing torque on the plank. We also have the mass of the actual plank, which will be causing torque. And I'm just going to draw it here so that you can see that we're talking about the mass of the plank. So we have the mass of the cat and we have the mass of the plank. Those are both affecting our torque. So our net torque is going to be, oops, that should be an equal sign. It's going to be torque 1 plus torque 2. And recall that our torque is going to be the force times the radius, or in this case, we're talking about distance, so I'm going to write D. So the force, we'll do the cat first. The force from the cat is caused entirely by its weight. So instead of writing F, I'm going to write mg. And this is going to be the distance of the cat, which has been labeled as distance 2. I guess I should have done this the other way, but it doesn't matter. And the second one is the weight from the board. So I'm going to do the same thing, mg, plus the distance that we see of, well, the center of mass to the left of the sawhorse. So that's going to be our second distance. And we know that all of this is going to have to equal 0 because our sum, the net torque, has to sum to 0. Now let's see what's going to happen, because one of these is going to need to be negative and the other is going to need to be positive. Remember, it's the clockwise direction that is negative and counterclockwise that's positive. So if this cat, we're just talking about the cat alone, if this cat were heavy enough and this board began to move, we know it would begin moving in the clockwise direction. So this one's going to be negative. And if it were this opposite end, it would be going counterclockwise. So that's going to be positive. Okay, so negative for the torque from the cat and positive for the torque from the board itself. Now that we have that, we can plug in what we know. And remember, we're solving for the mass of the cat, so we can rearrange this to actually solve for the mass of the cat. I'm going to differentiate. Here's mass of the cat, and we know the mass of the plank is a capital M, so I'm going to make this a capital M. That way it'll be easier to figure out. So let's rearrange this. And when you rearrange this equation, you should find that the mass of the cat is going to be equal to the mass of the board multiplied by distance 1 over distance 2. So the distance of the board and the distance of the cat from the center point. Plug in all of your information. So M equals, this is 6 kilograms. Whoops. And this information, D1, is 0.850 meters divided by 1.11 meters. So the mass of our cat is going to be 4.59 kilograms. So a fairly normal sized cat, that'd be around 10 pounds. And that's how you'd find the mass of the cat, given all this information. So it's not as complicated as it might have seemed, especially when you isolate the cat or you isolate the board and consider what's happening separately and then bring it all together. Okay, now this problem, again, none of these are super involved problems. We just have to stop and think about what's happening. And I have provided the sketch for you. So we see this person standing on a ladder, as shown here. The floor is rough, and because of that, we see both a normal force and a friction force on the ladder. And then the wall is frictionless. So it only has a normal force, which is perpendicular. So we want to figure out the magnitudes of F1, F2, and F3, and here is all of the information we've been given. So where do we go from here? Well, just like in the previous problem, we know that the net torque, whatever all our torques sum to, is going to have to equal 0. So let's consider what's happening with the individual forces. Okay, so we have force 1 here, force 2 here, and force 3 here. Okay, so forces 1 and 2 are acting on the same area. So let's put those together. And then force 3 is here, and we see this woman's weight here. So we have a lot going on. Take a moment and see if you can figure out what to do next just using this information and this information. And let me erase some of this. I'm so sorry, so that you can actually see it. Okay, there we go. So take a moment, try to figure this out, and hit play when you're ready. Okay, so we have our axis here, which means the forces that will actually cause torque are here and here. So the weight and then this force number 3 from the wall. So let's write down what we know. And again, this is our axis. So we're considering everything rotating about this axis. If this third force acted alone, it would be pushing this way, which is counterclockwise. So this would have a positive torque. And let's write that down. So force number 3, which we don't know what it is, times the distance it is from the axis, which in our case is A. See, right here, A. And that's the positive one. And then this second force, the force from the weight, if it were acting alone, it would be pushing her this way, clockwise. So that's going to be minus, and we know that force is mg. And it is acting at a distance b. Okay, so if we know that this equals 0, and we know all except F3, we can easily solve for F3. So F3 will just equal mg times B divided by A. We can plug in what we know. We see that the mass is 85 kilograms. We know gravity, 9.8. And then B is 0.7. Ooh, 0.7. And A is 3.8. Okay. So F3 is going to be about 150 newtons. Okay, so we found one of them. Now we need to figure out F1 and F2. Well, we automatically see that F2 and F3 are clearly pointing in the X direction, and F1 is in the Y direction. So we're going to have to separate this into the individual components, the X and the Y components. So let's go ahead and start with the one that we have two of. So F2 and F3. We know that together they must sum to 0. So, how do we know that? Well, this ladder is not moving right now. So F2, and if it were, F2 minus F3 equals 0. We already have F3, so this one's going to be really easy to solve. F2 minus 150 equals 0. That means that F2 also equals 150. Okay, so we now know that F3 is 150, and that also equals F2. So we have these two pieces of information. Now we just need F1. Well, F1 is in the Y direction, and we also have this force of weight in the Y direction. So F1 minus mg, so F1 is pointing upward, it's positive, mg is down, so it's negative, equals 0. We already know what the weight is, so we're just going to plug in that information, and you will find that F1 is equal to 830 newtons. So F1 is 830 newtons, and F2 and 3 are equal at 150 newtons. Okay, so in this next one, I did not flip the slide. Okay, this is a concept problem, and I'm going to give y'all a moment to read this over, think about it, and hopefully your response will be correct, but I'm going to go over that in a moment. Okay, I realized that I forgot to include the drawing, but I drew it down here. So here's the mallet. Here's the top part. This is part 1, and we're imagining it gets cut right here where it is suspended. And there's part 2. Okay, so with that, you can pause again or keep listening. It doesn't matter. The answer ends up being that piece 1 has the greater mass, and the best explanation is here. Well, if you're wondering why, that's because we can consider a torque in 2 ways. It could either have a short radius and a large mass, or it could have a long radius, a large radius, and a very small mass. And either way, you would end up getting the same torque. So if we know that it is suspended here, and this is a very short radius, we know this mass must be greater. And this is a long radius, so its mass must be smaller in order for this to balance out. And I think this one is easier to conceptualize than some of the other ones. You might have actually experienced this yourself or used this in real life. So this one should make a lot more sense than some of the other conceptual examples we've done in the past. So this is our answer here. Okay, and this time we've got 2 parts, A and B. And we're going to be finding the angular momentum in a DVD and then again with a motorcycle. So make sure you have your moment of inertia equations near you because you're going to be needing those and all the equations from this chapter as well. And I will be back to work this problem in a moment. Okay, so for part A, I'm not writing. This is going to be the easy part because it tells us that we're going to consider the DVD to be a uniform disk. Well, if you pull the information for moment of inertia, for angular momentum, we know that angular momentum is the moment of inertia multiplied by the angular speed. Well, we're working with a uniform disk, and if we refer back to that moment of inertia equation chart, we know that for a uniform disk, this is going to be equal to 1/2 mr squared. So let's replace I with 1/2 mr squared, and we'll find this. Okay. Now let's plug in our information. So this is going to equal 1/2 multiplied by 0.010. Oh, I'm sorry, I forgot to mention that. This is given to you in grams, but all of the equations we work with need to have units with kilograms. So you've got to convert that mass into kilograms. 0.0600. We had to convert centimeters to meters. So centimeters needed to go to meters. That's squared. And then we know that the angular speed is 125 radians per second. Okay, and this would equal 0.00360 kilogram meters squared per second. So this is what our angular momentum will be for part A, for the CD. Now we need to do it for part B, and I'm going to see if y'all can do this one. Treat the motorcycle as a point, as a particle, and go from there. So press pause and then hit play when you're ready. Now we're going to do part B, where we are considering the motorcycle to be a particle. When we do that, angular momentum is r, so the radius times mass times velocity. Let's plug in all the information because we have all of this. So the hardest part of that was just knowing to use this formula. Once we know that, it's simple because we already have this information. So there's the radius. We need the mass, which is already in kilograms. That's nice. And the speed, which is 8.92 meters per second. So L, the angular momentum here, is going to be 39,800 kilogram meters squared per second. Or you could say 3.9. Oh, what am I doing? 3.98 times 10 to the fourth kilogram meter squared per second. Okay, so that's what your answer would be for part B. Moving on to this next problem. We are looking at a goalie and a defender in a game of hockey. And here we're given a nice image, so a nice picture of what's happening right here. We're given quite a bit of information, and we're told which expression to use. So we are going to find the angular momentum in part A. In part B, we're going to find the moment arm for the defender. And in C, we're going to check that the angular momentum can also be given by this equation that we see here. All right, let's get started with part A. So for part A, we are paying attention to the defender right here. And we want to know the angular momentum as measured by the defender. So the defender is clearly viewing this puck at an angle, which means we're going to have to use the angular momentum equation that factors that in. And that is L equals RMV sine theta. So we can't just use L equals RMV. This, though, again, was the most difficult part, was just making sure you use the correct equation. But once you choose the correct equation, this is very straightforward. Let's just plug in all the numbers. Our radius is 1.45 meters. The mass is 0.170 kilograms. And the velocity is 4.42 meters per second. So we were told all of that. And then we have the sine of 2.5. So when you do this math, you should find that the angular momentum as measured by the defender would just be 1.04 kilogram meters squared per second. So there is part A. Okay, part B. So take a look at that equation sheet yet again, and we want to find the moment arm for the defender. Remember that the defender is viewing this puck from an angle. So we have to incorporate that. Well, the equation for that is right here. And since this is the thing we're calculating, moment arm, and we just need the radius and sine theta, which we have both of. Radius is 1.45 meters multiplied by sine theta, 72.5. So that equals 1.38 meters. Okay, so that part's not bad. Now, part C, final part, we want to check that the angular momentum, L, can also be given by this equation. So, to find that out, let's plug in our values. And I'm going to do that right up here. I think y'all should be able to see it. So we just found moment arm, which would be 1.38 meters. We know the mass, which is 0.170 kilograms. And we know the speed, which was 4.42 meters per second. When we calculate that, I'm going to put this down here, we'll find that L equals 1.04 kilogram meters squared per second. So it is the same here and here, which means angular momentum can in fact be given by this equation as well. So we've completed part C. And the final question, I'm going to change colors. We are talking about a star. Astronomy is very interesting. And so I was excited when I ran across this problem. So we have a star and it has a particular radius, and we know what its angular speed is. We want to know what the final angular speed would be if the star collapses down to a radius of 20 kilometers. So still a massive number, but not nearly as massive as its previous size. All right. So let's consider, we're thinking of a before and after scenario. Something we know before and after is that angular momentum will have to be conserved. Angular momentum will have to be conserved. And that means that the L before and the L after must be equal. So that gives us a good starting point for our problem. Let's go ahead and use the fact that we can replace, okay, so here we go. I, moment of inertia initially, and our speed initially is equal to our moment of inertia finally times the speed. finally, at the end, our final speed. Okay, this is a star, so we can go ahead and treat this as a uniform sphere, and we were even told that. And when you do so, if you look back at that equation chart, you'll find that I is equal to 2/3 mr squared. Oh, not 2/3. I'm so sorry. 2/5. Well, that was almost a very bad mistake. 2/5. Okay, my apologies. So we can use this and plug it in. Let's go ahead and replace the I in each case. So we're going to get 2/5 mr squared omega initial equals 2/5 mr squared. And this is, I guess I should make note of this. This is our initial. This is our final. And then our final speed. Some of this information is going to cancel out very nicely. So let's get rid of the parts that cancel out. So this is going to cancel. Mass is going to cancel. And that's going to leave us with radius and angular speed before and after. We want to know the final angular speed. That means we're solving for this. So let's rearrange our equation so that it is easy to see. And our final speed is equal to our initial radius squared divided by our final radius squared multiplied by our speed initially. So let's plug everything in. Our initial radius is 2.3 times 10 to the 8 meters. Okay, we need to be consistent with our units. So we have meters here. This is given in kilometers. Let's write it in meters. And in meters, that would be 2.0 times 10 to the 4th. Oh, I'm sorry. These are both squared. And then multiply it all by the speed, which was 2.4 times 10 to the negative 6 radians per second. And you should find that the final angular speed is 320 radians per second. And that's all we need for that problem. So if you have questions, please reach out to me or post in the discussion board that is in Canvas. You will have a test next week over only chapters 10 and 11. Just as a heads up, I thought I would let you know that. So make sure that if you have questions, you are asking them. And thank y'all for watching.